Oh, ah, these things don't work. Howdy. Oh wait, I gotta do my joke, right? Bond, chemical bond. So, chemical bonds. Here we go. So we'll have to show all kinds of things over there, but let's start with electron configurations and how these chemical bonds come into play, our understanding, and how we're going to use them. So let's just start with some atoms here. Let's start with this atom, and it's got some electrons. I'm going to put some dots here. All right. Hey, which element is that? Let's see. 10, 12 electrons. That'd be magnesium. Wow. All right. And then I've got another thing over here. And it's got some electrons. And 1, 2, 3, 4, 5, 6, 7, and 8. Oh, let's take those away. All right. So there these guys are. They're in the wrong proportions. This one should be smaller, but whatever. Who cares? A bond takes place when these things bang into each other. It is the outside layer that matter. So if I was looking at this one, I'd have 1s2, 2s2, 2p6, 3s2. And this one I'd have 1s2, 2s2, 2p6, 3s2, and oh, we're almost out of space. Gonna squeeze it. 3p, 1, 2, 3, 4, 5, 6. No, that doesn't add up. So 2, 4, 6, 10, 12, 16. That should be what I got. Yep. And 12 should be what I have here. Yeah. Excellent. So yeah, the sulfur and the magnesium. And they're getting ready to interact. We want to be able to predict what kind of interaction they're going to have if they were to bang together really strong. And so what we care about then is the electrons on the outside layer, and those are called valence electrons. Those are the ones on the outside. In other words, this outsidemost layer, that's the ones that have the biggest N number here. So this one has 2 valence electrons. And then over here, when I'm looking at my other atom, it's got the 3s2 and the 3p4, so it has 6 valence electrons. All right. So we can predict all kinds of things by this, and there turns out to be a pattern on these. And it has to do a lot with how many are in the outside, and it also has to do with their electronegativity. But let's get an idea of these, and that is because if I look at, oh, let's pick on neon. So out of room here, let's draw neon. So it's got terrible. 1, 2, 3, 4, 5, 6, 7, 8. And so neon, you get your nucleus and electrons around the outside. All right. If I were drawing them the scale, nucleus would be way just a tiny little wee dot in the middle. All right. And so here's my neon. It's one of the noble gases, and its outside layer is full, completely full. And neon doesn't react very much. And then if I go and I look at argon, oh man, so way out here, little dot, a circle, another circle, and another terrible circle. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. All right, 1s2, 2s2, 2p6, 3s2, 3p6. That would be my argon. Well, it turns out that these are incredibly stable, unexpectedly stable. Just, man, are those noble gases stable? And the way I like to think of it is they're kind of like the cool kids on the periodic table. And all the other elements want to look like them on the outside. That's what determines you cool. Back in the old 80s flicks, right? It was who had the leather jackets and maybe that was 50s. I don't. Man, it's hard to tell what kids think of as cool nowadays. We all know now it's the inside. But in terms of chemistry, it's these outside layers. And so they want to look like the nearest noble gas. And so if we can describe what's going to happen here, well, there's two ways we can get there. I can have this compound gain, notice it's missing 1, 2 electrons to be like argon, and then it would be stable. Its outside would be very happy. And then this one, it would have to gain 1, 2, 3, 4, 5, 6 electrons to get to argon. Ooh, that's a lot of work. Or it could lose 2 electrons. And let's see what happens if I lose 2. This whole outside layer is now empty. And the new inside layer, assuming I do my right number of dots, 1, 2, 3, 4, 5, 6, just missing a dot. There it was. Ha ha. All right. So now it looks like neon. It's also happy. So we'll keep this in mind. We're trying to get to the noble gases, and there's two ways of doing it. We can get up to 8, which is what all the noble gases end up having, or we can get down to 0, which exposes the next layer down. So we need a better way of doing this without having to draw all these circles and without having to redo our electron configuration every time. And so these valence electrons, we can tell by using the A numbers. So it only works for the representative. So our A numbers. In other words, if it's group 1A, it has 1 valence electron. Valence electron. If it's in group 4A, it's going to have 4 valence electrons. All right, and so then 7A would have 7. Now, this only works on the representative elements. It does not work at all on the transition elements or the inner transition elements. It only works on the representative elements. All right. What if you've got a periodic table and it doesn't have the A's? It's a modern periodic table. So there we can do 1 and 2. Those are easy. It's still 1 electron, 1 valence electron, and 2 for group 2. So let's do this, 1 and 2. All right. And then we'll go to 13, and it has 3 valence electrons. And group 14 has 4 valence electrons. Now, what we're doing is we're taking our 14 and literally subtracting 10 to get 4 valence electrons. Now, these 10, if I looked at a periodic table here, so here's my A numbers. We're going to ignore those. We're looking at these. So when I'm at 14, we could take these Roman numerals if you have it. So this, since it's an A, it's 4A, it has 4 valence electrons. But if we don't have it, we can go by this 14, and the 10 that we're subtracting out are actually these D's. And so they haven't filled at the point that we get here. So we're just going to subtract those out. Remember, these are all one layer down. So if I go across here, this is 4S. These are the 3D pin. To the next layer down, they're not part of the valence electrons. The S's are. And then over here, I'm at the 4P's. Similarly, when I do the 3S and the 3P's, those fill And then we actually fill the S's before we start filling any of these d orbitals. They're there, but they're sitting there empty. All right, we haven't filled them yet. And so we're just going to subtract 10 from here. But it's actually way easier than that. If I want to do group 17, I just ignore the 7 and say this is 7 valence electrons. That's simple, okay? So then we can look at group 18, and it has 8 valence electrons, except helium has 2. Keep in mind that's because helium doesn't have any p orbitals. It doesn't have those p6. There's no such thing as a 1p. There's only room for the s's in that first energy level. Those, when I drew my own circles, they only had 2 dots on that first layer. All right, so a lot of stuff going on here. What we can judge by this is say everything's trying to get to the noble gases, group 18, which has 8 valence electrons except for helium. 8 valence electrons except for helium. All right, so this is called the Octet Rule. And we will find many times this term is super important. It's so important. There's all kinds of different ways of stating it. All right, we can say that we can say atoms react to obtain 8 valence electrons for helium. We can say atoms react to become, I'm going to use a fancy word here, isoelectronic with the nearest. In other words, you can go forward, you can go backwards. It's not necessarily the last one you pass, like when we did electron configuration. Noble gas. Okay. Now this kind of helps us to come up with a plan here. And so either we're trying to get to 8 or down to 0. 2 if we're talking about helium, all right, or we're trying to follow them on the noble gases. So we want to keep in mind on this one, all right, you move forward a box on the periodic table, that's gaining an electron. Move back, it's losing an electron. Okay, all right, easy enough. So how do we use this? Well, we look at, let me click on our table here. So let's look at nitrogen. So nitrogen it's in group 15, so it has 5 valence electrons. I'm going to write that down. 5 valence electrons. And so we can ask ourselves, is it easier to gain 3 to get to 8 or lose 5 and get to 0? Or we can look at these boxes and we say it can move forward 1, 2, 3 to be at neon, or it can move back 1, 2, 3, 4, and then it wraps around and we'll be back at helium. So we want to know what makes sense. What sounds easiest to us, we can gain 3 electrons, or we can lose 5 electrons. Okay, we could draw our electron configuration, we could draw a picture of it, but we don't need any of that. We can easily tell, hey, this looks like our winner. That's the one it wants to do. And so we can predict that nitrogen will gain 3 electrons. So therefore, it'll be a -3 if it's with something. And so nitrogen will like to be a -3 if it's with something. Now we can do a similar kind of approach. Oh, let's pick on calcium. Calcium has two valence electrons. It can gain 6 or lose 2. So it's going to lose 2. If it loses 2, it goes back to argon. If it gains 6, it'd go up to krypton. Remember, we're skipping right over those d orbitals. We don't know anything about those transition metals. This does not work for them. Okay? And so, if it lost 2 electrons, this will be a +2 charge. It'll now have, calcium would have 20 protons and 18 electrons because it lost 2. So, all right, we went back to, so it had a +2 charge. That's how we use the octet rule. All right. Now, octet rule really does define a lot of things for us, and it gives us some patterns we see. So I tend to call this my chemistry man cards. Because I use these more than I get to use my man card when my wife takes it out of her purse and says, "Here, go be a man for a minute." All right. My man cards here. So here we go. Group 1. Except hydrogen. Hydrogen does some wonky stuff. We'll talk about it later. All right? Except hydrogen. Group 1, except hydrogen. Always +1 when with something. Now you have to be careful. That means if I drew a potassium, right now it's charged. There's nothing up here. So its charge would be 0. If there's nothing indicated. But if I put this potassium with something else, then I know that that potassium is a +1. If it's with something and it's got group 1 except hydrogen, it's always a +1. Oh, man, I like that. All right. So let's get another one. Group 2. Always, well, I can't spell always today. Always +2 when with something. All right. And we can even talk about group 17. I mean, group 2 was that was the alkaline earth metal. Got to know that name. All right, group 17. That's our halogens. Likes to be -1. Likes to be, that's, I mean, terrible. Likes to be. Always, it was a lot stronger. So it likes to be. So it's going to actually depend on what it's with. Oh, so that brings us to some of the others. So carbon and nitrogen and oxygen. We can make some rough predictions on them. Oxygen has 6 valence electrons because it's in group 16. It wants to be a -2 to gain 2 electrons. Nitrogen wants to be a -3. Carbon, it's in trouble because it has to either gain 4 or lose 4. And neither one of them is very easy. And so it's going to do something completely different. So let's get into the bonds that happen here, the bonds we can make. There's actually 2 categories, and one of them has two subcategories. Let's talk about ionic bonds. And our key word here is transfer. So keep in mind, if you transfer money with the bank, one of you gains it, one of you loses it. Here's we're going to be transferring electrons. And so one gains electrons, one loses it. So if I gain an electron, that makes a negative charge. If I lose an electron, that makes a positive charge. Easy enough. Sounds backwards. Sounds backward. Keep in mind, electrons have a negative charge. All right. So we have names for these. What's this word ion? So an ion is an atom with a charge. Atom with a charge. All right. They come in two flavors. Anion, a negative. It's got an extra N for negative. N for negative. A negative ion. It's right there in the name. All right. Anion, that's our negative. And then we have this cation. All right. Now, I learned this all kinds of crazy ways, but let's just show you the easiest one here. Man, I wish I'd known this when I was a student. You see a positive, turn that T into a positive, ion. You see a positive ion. Positive ion. All right. Easy enough. So we've got ionic. We'll get a plus, an atom that has a plus, and we'll get an atom that has a minus, and then they're opposites, and so these attract. And that forms our ionic bond, is the attraction forces between these. All right. Okay, so ionic, then we're transferring. The next ones then we have to worry about are called covalent. And they come in two flavors. But here's my key word for covalent. They share electrons. All right, now our two flavors here, we've got nonpolar covalent. All right, so let's translate that. This is equal sharing. Both of them want it the same. They share it equally. All right, and then we've got polar covalent. Or unequal sharing. So we can use language on polar covalent that one of them has the electron longer or more often. You can also say the electrons are closer to it. Both are actually correct. All right, it's kind of going on at the same time. So unequal sharing and equal sharing. Now, here's where the confusion lies. In these chapters, the books will refer to ionic versus covalent, and they're talking transfer versus sharing. And they spend a lot of time looking at that. And then later they get focused in on covalent, and they'll say covalent versus polar covalent. And so they're talking equal sharing versus unequal sharing. So what I do, this non-polar covalent for equal sharing, instead of you just calling that covalent like many books do, when I want to talk about this specifically compared to the others, I'll say non-polar covalent. If I just say covalent, it's including both of these. All right. So when we share these electrons, most people are introduced this with the model of here's my nucleus and it's got all these plus charges. There's my nucleus. And here's another nucleus and it's got positive charges. And if I put the electrons in the middle and they're negative, then they tie these nuclei together and they hold them together. It's not, I mean, it's a great picture. It gets the light bulbs on. It's a great idea to kind of think about it. We'll draw a lot of our stuff based off of that model. Not at all. What's really happening, really, the electrons kind of being split around. They orbit around both of them. We're going to look at, they just hold them together. Okay. Now, we want you knowing these terms. Easy enough. But we got to be able to predict these. And to do that, we use electronegativity. And so remember, electronegativity was how much an atom wants. How much an atom wants an electron, both to keep the ones it has and to gain new ones. Now, if I go in the book, I can pull up tables on electronegativity, and we can do all kinds of this term you'll see this term, difference in En. All right. So difference is then going to be our difference or change. And so it's going to be usually we think in final minus initial, but we just subtract the two electronegativities. And what we find is fluorine is the highest at 4.0, and cesium way over here is the lowest at 0.9. Nope, 0.7. All right, so the biggest difference we could have is 3.3. The smallest difference we could have, if I pulled up one of those tables, you would see it, but it's actually even easier if I do hydrogen and hydrogen. So this is usually 2.1 and 2.1. They both exactly have the same electronegativity. And so I would predict that difference would be 0. So the way that, if you were to try and do it with these numbers, you would look at the difference in electronegativity, and the top of this would be 3.3, and the bottom would be 0, and they split it in a couple of places. And the problem is they keep changing these places because they're trying to match the data. And so what we find is the numbers I remember is 0.5 and down is non-polar covalent. These want the electrons the same and or close enough, and so they share close enough. If I go 1.9 and up, so including 1.9, this would be ionic, and then in the middle we'd have polar covalent. And not only do they move these numbers, but it's kind of a spectrum as we move across. And so this misses some. This gets some wrong and gets some, they keep changing the answer. It's hard to come up with something, that predicts everything doing that way. So if that's going to miss some and you got to look at those numbers or memorize those numbers every time, then let's go with a different approach. And the approach I'm going to use is looking at my periodic table. So I'm going to sketch out my periodic table and kind of get an idea of where things are. So I've got all these things. If I looked at a list, hydrogen at 2.1 does not fit anywhere over here. It actually fits over here. And that's our first kind of thing that I'm going to write down. So first thing I'm going to do is I'm going to say move, pin's trying to down me, move hydrogen above the B and the C. In other words, it goes right above this line, above the boron and carbon. So right in here, that's where my hydrogen is going to be. All right, now I can look at where things are. So I've got my staircase. If I cross the staircase, so if I go across the staircase, typically they use language like a non-metal and a metal. But if I cross my staircase, then it's going to be ionic. They're going to be far apart. And so the thing over here will be closest to cesium. It'll have the lowest electronegativity. The one over here, my non-metal, will be closest to fluorine, have the higher electronegativity. Keep in mind, the atom that wants it the most gets it. And so the one that's over here closer to fluorine will be my negative, and the one over here will be my positive. So we're now then going to say, so there's this, that's number one here. Here's number two. So we cross the staircase. And that tells me it's ionic. Now remember, I had to move that hydrogen over. It's above the carbon now. So hydrogen and oxygen are not crossing that staircase. Okay. So then the next thing we're going to look at is when we don't cross the staircase, what do we have going on? So if I look at where they're not touching, so they're not touching, and touching, I mean side to side and up and down. Don't count corners. Side to side, up and down. So if they're not touching, but we don't cross the staircase. In other words, they're close, but not touching. So not touching. we say touching, don't count the corners. All right. So they're not touching. Don't cross the staircase. They're going to have similar electronegativities, but they're different enough that they don't share equally. In other words, these are polar covalent. A good example of this is our hydrogen and oxygen. Hydrogen is up here, and now you can see it's not touching the oxygen, so we don't have to cross the staircase though, and so these would be polar covalent. And the one that is closest to fluorine then gets the electrons more. And so that's going to be the one that has more of a negative charge. It's not an ionic charge. It just has it more. We have a term for that, a partial charge. All right. Now, our last case then is, what if they are touching, like nitrogen and oxygen? They touching side to side. So touching is our last case here. If the boxes are touching, that's going to be nonpolar covalent. You have to be careful in many of these questions they ask, is the bond polar or nonpolar? And so you have to be careful. If they're touching, then no, they're not polar. They're nonpolar, right? If they're not touching, then yes, they're polar. You got to be careful. That language shows up in lab a couple of times. So this is how we can use our electronegativity to tell what kind of bonds things will make. Okay, this is going to be very helpful in when we go to name things. It's going to be really helpful when we go to do talking about the properties and predicting everything all the way up until we start looking at melting points and boiling points, all kinds of properties. We can tell by just saying, what kind of bond do we predict things to make? So we'll come back and we'll revisit this some more later, but we'll go ahead and end this one here. And just don't forget to move that hydrogen. You cross the staircase, it's ionic, which means a transfer. The one that's closest to cesium will be the one that loses the electrons. That's your positive charge, your cation. The one that is closest to fluorine will gain the electrons. It wants the electrons more, so it gains them. And that makes your negative charge your anion. Okay. Then when you get down here, we don't have those terms anion and cation. And so if we're not crossing that staircase, they're either going to be touching or they're not touching. If they're not touching, they're polar covalent, unequal sharing. That idea of polar, that comes from a magnet, and you can draw a line and separate the north side and the south side. So when I have something like a hydrogen oxygen bond, the hydrogen is further away from fluorine. So we use this little symbol here, a partial negative and a partial positive. And we can draw a line to separate the positive from the negative sign. Now, when they are touching, it's nonpolar covalent. There's none of these charges. They're sharing perfectly equal or close enough. Okay. A good example of that carbon-hydrogen bond. Always nonpolar covalent. So even if you were doing the math method, it comes in at 0.4. So anytime they get to doing those numbers and they get to playing with them, they never go below 0.4 for our nonpolar covalent. Whoa, man, that's a lot. Just take it easy. It's not difficult. It just takes practice. You've got to practice this stuff. Just keep in mind, it's a process. All right. So we'll catch you on the next one.